I want to show you an example of solving the example we solved in the last video, but doing it using Laplace transforms. And this is just to get a little more practice with Laplace and to show you kind of when this is going to be helpful and when it won't be. So it really depends on what's most convenient in the moment, but it's good to be comfortable with more than one method for solving this. So let's try using Laplace to solve this. We'll need a couple of reminders. So you should have your Laplace transform sheet handy. But don't forget that y double prime, or I should say it this way, the Laplace transform of y double prime equals s squared times y minus s times y of 0 minus y prime of 0. And the Laplace transform of the first derivative is the similar form with sy minus y of 0. We've talked about that before, but just as a reminder, there's your Laplace transforms. We'll need a couple others later on when we get to the end of the problem, but for now this is enough to get us started. So the first thing we do is take the Laplace transform of everything. So we have, pulling the constants out, we can take the Laplace transform of each term. We have the answers for the second derivative and first derivative. So this is going to be 1/4 s squared y minus 1/4 s y of 0 minus 1/4 y prime of 0 plus sy minus y of 0. That's for this term here. And then for this term here, we just get capital Y. So plus 4 capital Y, and the Laplace transform of 0 is just 0. So as always, we're going to solve for capital Y, so we need to clean this up a little bit. Remember that y of 0 equals negative 1/2, and y prime of 0 equals negative 1. That was the setup for the problem. So we can plug those in, and we'll get 1/4 s squared y minus 1/4 s times negative 1/2 minus 1/4 times negative 1 plus sy minus negative 1 plus 4y equals 0. And then we'll collect on the left side all the terms that have capital Y in them. So we'll have 1/4 s squared plus s plus 4 all times y. So I collected them and then factored out the y kind of all in one step. And then the other terms we're going to collect and move to the right side. So as we move these over, the negatives become positive, so we're going to have, what do we have, negative 1/8 s minus 1/4 and minus 1, which simplifies to minus 5/4. Back here, this should be, sorry, this should be a negative 1/2 instead of negative 1. Sorry, I used y prime of 0 instead of y of 0. So let me fix that. This here is 1/2. All right, so then this simplifies. The minus 1/2 and minus 1/4 is negative 3/4. Okay. So this, if we solve for y, we get negative 1/8 s minus 3/4 over 1/4 s squared plus s plus 4. Now just to simplify things a little bit, I don't like dealing with this 1/4 in front of the s squared. So I'm going to multiply, just to clean up the algebra a little bit, I'm going to multiply the top and the bottom by 4 here to make this quadratic easier to work with. That's kind of the idea. Just to make life easier, I'm going to do that. So then we get y equals negative 1/2 s minus 3 all over s squared plus 4s plus 16. All right, so we want to break this up. We want to simplify this and get it into a form that we can work with. But we got to deal with this quadratic down here. Now, to deal with this quadratic, that's not one that's going to factor nicely. And so if we start trying to do a partial fraction decomposition, we're going to get stuck at the first step where we try to factor this. Not only that, but if we did partial fractions and you can't factor this, then the form you would set up would just be as plus b over this same denominator, and it would sort of trivially work out to look just like this. So the point is, it can't be broken down by partial fraction decomposition in this form. So that's why I wanted to show this example, is just to show you kind of what can happen when you start doing a Laplace transform problem if it doesn't look like the ones we've done before, where we could just use partial fraction decomposition. So instead, we have to go back to another algebraic technique that you've seen a long time ago, where we're going to complete the square on this. And if you've forgotten how to complete the square, we'll review real quick what it looks like. But it's an algebraic technique that we don't use very often, but when we need it, it comes in very handy. So it's a good thing to know how to do. And of course, it's really the backbone of the quadratic formula. That's how the quadratic formula is developed. So you have to take this s squared plus 4s plus 16 and complete the square. In other words, we want to build this as a perfect square and then some extra stuff that fits into this 16. So the setup here is, if we're going to have a perfect square, this is sort of the starting point for a perfect square. And we want to figure out what perfect square has that in common. In other words, what perfect square starts out as s squared plus 4s. And the one that does, in other words, if you think about this coming from this perfect square, so we're trying to figure out what this question mark is. If you think about this, when you square this, when you expand this out, you get s squared plus 2s times this. So the mystery number is just going to be half of this coefficient of s. And that's kind of the key to completing the square. Once you know that, it's just always half of whatever that coefficient of s is. So the one that it looks like is if this were s plus 2 squared. That's the perfect square that we want. And if you factor this out, or expand this out completely, you would get s squared plus 4s plus 4, right? So the perfect square we want is s squared plus 4s plus 4, which looks similar to this, except it's not exactly the same. We're off by a little bit. And if you look carefully, if we break this 16 up, we can split off a 4 to fill out the square. And that's the idea of completing the square. You can split off a 4 to complete that, and then what's left over is a 12 that just gets added on. So basically, at the end of all this, we end up breaking this down and rewriting it as s squared plus 4s plus 4 plus 12, and all of this is going to be this perfect square. So I'm going to erase kind of all this extra stuff on here and just point out the details we actually need. So if we erase all this, this is equal to s plus 2 all squared. Now you'll see in a minute why this is helpful, but again, just to reiterate completing the square, what you do is you look at this number here, the coefficient of s, or x, or whatever your variable is, divide it by 2, and then square it, and that tells you what the missing piece is in the perfect square. And then whatever you need to do to this extra constant to make it work, you can think of it as like adding and subtracting 4, or a couple different ways of rearranging, but you break off the piece that you need, and then you'll have some leftover like this. So that's what that denominator looks like. So what this turns into is s plus 2 squared plus 12. Now why is that helpful? The reason that's helpful is if you look carefully back at your Laplace transforms table again, you should see a couple that look like this. So the Laplace transform of this combination of the exponential And the sine function, e to the at sine of bt, looks like this, b over s minus a squared plus b squared. And that form right there is what we're looking at right here. That's the connection that we're going to make, because that's the denominator on this piece, right? So that denominator we're going to rewrite in this perfect square form, because now it matches something in our Laplace table. So I wanted to show you this example because, again, this algebra gets a little bit tricky, and that's kind of what makes Laplace problems hard, is the algebra. But there are ones where you run into a situation where partial fraction decomposition isn't what you want to simplify something like this, but instead you can complete the square and it'll look similar to what you see here. So now the rest of the problem is basically figuring out how to fit it into this form. We also need the other one with the cosine, and we'll see why in a second. So this looks like s minus a over s minus a squared plus b squared. So all we have to do now is figure out how to break this down and fit these forms to something using this. So maybe it'll help if I rewrite y using that denominator. So y is negative 1/2 s minus 3 over this right here. So the key to this, to figure this out, is to look at this denominator and look at this denominator and figure out what the values of a and b need to be. So pretty clearly you should be able to see that if we let a equal negative 2, s minus a squared will look like s plus 2 squared. Right, so we've got half the puzzle. And then the other half is to figure out what b is. And since b squared equals 12, b just equals the square root of 12. Or we could write that as 2 root 3, if you simplify, right? Because there's a 4 and a 3 in here, so you can pull the 4 out and take the square root and get 2. So we've got a and b figured out, and then it's just a matter of taking this numerator and kind of massaging it a little bit into the form that we want. So what we're looking for is we're looking for one of these pieces to have the numerator of b, and the other one to have the numerator of s minus a. So that's where we have to get to, is kind of figure out how we can work this out to get the a, or get the numerators that we're looking for. And that's kind of, again, a little bit of a tricky thing to see the first time you do it, to see how to get the right constants in the right place. So what we're going to do is think about, okay, if we want to have, let's say we want to have s minus a first. We need to think about how to get that from here. So the first thing we're going to do is pull out the negative 1/2. We're going to break this off and factor it out so that we just have s instead of negative 1/2 s. All right, so we're going to take that negative 1/2 away. And then when we do that, that just leaves s here. And then if you look carefully, that's going to be, when we take away a negative 1/2 from the minus 3, that's going to be plus 6. Okay, so far so good. So we have that taken out, and that negative 1/2 is going to show up kind of in both places. So we want this one piece, the s minus a. We know that a is negative 2, so we want to have s plus 2 up here, which means we're going to break off in such a way that if I break this up and make this s plus 2, the rest of it is going to be 4. In other words, I've broken off a 4 here. There's a couple ways to see this. One is you could just think about split this 6 into a 2 and into a 4, because the 2 is the one we want, the 4 is kind of the leftover. The other way to think about this is that we want to have s plus 2, so you can just insert a plus 2 here, and then insert a minus 2 to balance it out here at the end. And then the s plus 2 goes here, and then the 6 minus 2 goes down here to become 4. So there's a couple ways to observe this happening, but at the end of it all, you have this setup here, where we've got the s plus 2 here. So we've got one piece that we want. We've got the cosine version fully finished. Now we just have to work on this version, because we want that to look like b over s minus a squared plus b squared. So we want to have, instead of a 4 up here, we want to have 2 root 3 up there. So that's kind of our next goal. And if you're not tired of the algebra just yet, we'll do one more step and then we'll have that. Maybe it's convenient now to distribute this negative 1/2. So I'm going to have negative 1/2 times this. And then here I'm going to have minus 2 times this here. So notice how I combine the 4 and the negative 1/2 to make negative 2 here. Okay, so I want to have b on top here, in the numerator here instead of 1. So what I'm going to do is just multiply here by 2 root 3, and then divide here by 2 root 3. That's the idea. So to get the b that I want, I'm just going to divide this coefficient out here by 2 root 3. So I'm just kind of adjusting these constants to be what I want them to be. So at the end of this long process, we get something that looks like this. Well, I can simplify this to 1 over root 3, and then here I have 2 root 3 over s plus 2 squared plus 12. So that's our value of capital Y, and at this point now we've got each of these in the form of something on our Laplace table. So we can immediately jump backward to our solution little y, and this negative 1/2 is multiplied by, that's the e to the at cosine of vt, using the values of a and t we have above. And the next one, we have minus 1 over root 3, and this one is the sine using the values of a and t, or a and b that we have above. So again, we got the same solution as we did earlier. I think you'll agree this method was much more difficult and much more trouble, but it was all just algebra trouble. And that's really where Laplace gets complicated, is in the algebra of things like completing the square, things like trying to work this system down to look like one of these. So you can run into problems like this sometimes using Laplace, and I wanted you to see at least one here in the notes and in the video, so that if you run across something like this in the homework or elsewhere where you need to use Laplace for some reason, you can do it this way. Obviously for this type of problem, we would probably do it a different way that would be easier, but it's good to see things like this that are a bit challenging and make sure that you can follow through the algebra like this. So that's using Laplace to solve this free damped vibration system.